Alright guys, in this section we're going to be discussing limits at infinity. We will discuss the end behavior of a function on an infinite interval. Remember how in a previous section we've discussed infinite limits. This is different, right? Before with limits that were equal to infinity, either positive or negative infinity. Now we're evaluating limits at infinity when as x goes to infinity, either positive or negative infinity. And we're going to see if we get a limit or if we get something else, or if the limit doesn't exist. So let's consider this function here, f of x equal to 3x squared over x squared plus 1. So it's a rational function. You have the graph here. Notice how as x goes to positive infinity or negative infinity, the function seems to be approaching the value of 3, right? So there's actually going to be an asymptote there. We're going to talk about asymptotes and the formal definition, horizontal asymptotes, later in the video. But we can look at the graph and kind of determine what's the end behavior on that infinite interval as it goes to either end. In this case, on both sides, it's approaching that 3, or we can confirm it or evaluate numerically. We can investigate what is actually happening as we go to positive infinity or negative. So as x gets larger and larger or smaller and smaller to either side, right or left, the function seems to be getting closer and closer to that number 3, right? You can see that on this table, right? F of x approaches 3 in this particular case on both sides. Now, we don't have to have both sides going to the same value or limit to be able to have a horizontal asymptote. But in this particular case, in this particular example, both sides, as x goes to positive infinity or negative infinity, f of x approaches 3. So here we have the definition of limits at infinity. If we let L be a real number, the statement that the limit of f of x as x goes to infinity equal to L means that for each epsilon greater than 0, there exists an m greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. In the same way, if we have the limit as x goes to negative infinity of f of x equal to L, we're going to have some number n, right, or some epsilon greater than 0 such that there exists an number n less than 0, so that f of x minus L, that absolute value is less than epsilon for x less than n, right? So remember that this epsilon, we're talking about neighborhoods, setting that for any given epsilon that you choose, as you see here in this graph, if we have a limit L and you choose some neighborhood around L, there's always going to be, for any given epsilon that you choose, there's always going to be a value m such that every x above that m is inside that neighborhood, right? And I'm talking about number 1 here on the definition. Similarly, if you want to do it on the other side, going to negative infinity, but it works the same way, right? So this is as x goes to infinity. If I make that epsilon smaller, I can move that m to the right and always guarantee that I'm going to have all my function values in that neighborhood. Here's a interactive sketch of that graph of the example that we had, 3x squared over x squared plus 1. So this was the function. And notice here I have a green point, a green dot on the graph here in red. And as I close in, as I make my epsilon smaller and smaller, so around the limit 3, I can always find, notice how that point is moving to the right in this case, so as x is going to infinity, I can always find an m, right, some point m, in the x-axis, such that every f of x is in that neighborhood that you see in between the dashed lines for all x is greater than that m. So no matter how small I make my epsilon, I can always find a number m such that for all x is greater than m, my f of x is in that neighborhood. And the same way works for if we go to the other side, in the opposite direction, the negative infinity, and showing the definition that we had. That happens because that function is actually getting closer and closer to that limit. In this case, it was 3. Now, here we have that formal definition for a horizontal asymptote. And we have the line y equal to L is a horizontal asymptote of the graph of f when the limit of f of x is equal to L as x goes to negative infinity, or the limit is equal to L as x goes to infinity. So it's either or, right? It could be both, like if we had on the example above, but it doesn't have to be. As long as we have one of these limits approaching some L, some real number, then that y equals that L, which is a horizontal line, will be a horizontal asymptote of this function. All right, so here we have a theorem for limits at infinity, and these are limits that we'll use all the time when evaluating limits at infinity. So every time you have a limit where you have a constant on the numerator and a power function of some x raised to some power, if you take the limit of an expression like that as x goes to infinity or negative infinity, that's always going to be equal to 0. And here on the second limit is valid only if x to the r is defined when x is less than 0. Okay, same thing for functions like e to the x or e to the negative x. If you remember the graphs of those exponential functions, they approach 0 as they went to infinity. So depending on which one you're doing, if you do e to the x as x goes to infinity or negative infinity without bound, that's equal to 0. Okay, in the same way for e to the negative x as x goes to infinity, that's equal to 0. And you can just verify that graphically or numerically, but it's, these are limits that you would use a lot when evaluating limits at infinity. Right, so here we have some examples at limits at infinity, and I want to do a comparison between these three. And notice how if you look at all three, they are very similar. You have to look very closely to see the difference, and the difference is in the degrees here. The exponent of that first term on the numerator is to the first power, and the first one on the second one is to the second power, and the third one is to the third power. That is the only difference. Everything else is the same. But you're going to see how that power is going to affect the actual limit here. So evaluating these limits, we're going to use a standard procedure, standard trick in algebra here, where you divide each term by the largest power function. In this case, notice how the largest degree is 2. We're going to divide each term by x squared. And when we do that, we get 2x over x squared. That simplifies into 2 over x plus 5 over x squared. Okay, all that over, notice how 3x squared over x squared, it simplifies into a 3, and then plus 1 over x squared. Notice how you now have terms that look like the first type of limits that we had in our theorem above, right? So all these theorems are going to go to 0 because you have a constant on top, right? If you were to take the limit of these terms individually, you have a constant in the numerator, right, and a power function in the denominator, raised to some power. All of those limits are equal to 0 as x goes to infinity. The only one that stays the same is at 3 because it's a constant. Limit of a constant is just a constant. So notice how after applying this ruling here, I get that the limit as x goes to infinity of this whole expression that comes out to be 0 over 3 is equal to 0. 0 over 3 is 0. The limit of 0 is just 0. All right. In the same way, we're going to use the same technique here to find this limit. We're going to divide each term by x squared. Because if we just try to plug in infinity, right, into the top and bottom in the original problem, we're going to get an indeterminate form. We get infinity over infinity, and that is inconclusive. That doesn't tell us anything. Now, remember that infinity over infinity doesn't mean the limit doesn't exist. So we need to do something else, some algebraic technique to be able to see if we can find the limit or determine whether it actually doesn't exist. So in the same way here, all those terms go to 0 as x goes to infinity, and we end up with the limit of 2 over 3, right? And that's a constant. Limit of a constant is just the same constant, so it would be 2/3 in this case. Now in this last one, we still want to divide by x squared, each term so that we get the bottom one equal to some constant there. So once we do that, you're going to see, so instead of doing x cubed, we don't necessarily want to divide everything by the power function with the highest degree, but the one that is going to eliminate the highest exponent on the denominator there. So in this case, it's still x squared. So after we divide everything by x squared, we get, in the numerator, we get 2x plus 5 over x squared over 3 plus 1 over x squared. So as before, these terms approach 0 as x goes to infinity. So we end up with the limit of 2x over 3 as x goes to infinity. And this is just a linear function, 2/3 of x, which as x gets larger and larger, that just goes to infinity. So in this case, this third one, the limit doesn't exist, it goes to infinity. So from here, we can identify some patterns here. All of these are limits of rational functions. And notice how the only difference was the degree of the top and the bottom. So we can identify some patterns here. We have some guidelines here for finding limits at plus or minus infinity of rational functions. And you've seen this in your algebra course, but now you see why. Having a formal definition of horizontal asymptotes, we can have now more rigorous guidelines for finding these limits in horizontal asymptotes as well. Notice how if the degree of the numerator is less than the degree of the denominator, the limit of the rational function is 0. If the degree of the numerator and the denominator are equal, then the rational function, the limit of the rational function is the ratio of the leading coefficients, as you can see there on the second example. And if the degree of the numerator is greater than the degree of the denominator, then the limit doesn't exist of that rational function. Right? You can see that. And that's going to happen every time you have scenarios like that with the degrees on top and the bottom. So remember that we use that to determine horizontal asymptotes as well in your algebra course. And just to finish up and come full circle here, you have also a formal definition for the infinite limits at infinity. So this is combining both, right? The infinite limits that we've done before and limits at infinity here. We have such limits that as x goes or approaches to infinity or negative infinity, the limit is actually infinity. Okay, so those would be infinite limits at infinity. When the limit doesn't exist or the function approaches, increases or decreases without bound as x goes to infinity or negative infinity, as x also increases or decreases without bound. But there you have it. Here we have just a couple examples of limits at infinity. They use other types of functions, such as transcendental functions like exponential functions or trigonometric or inverse trig. So you want to make sure you know the basic behavior of these functions. Sometimes thinking about the graph of these functions will give you an idea of what this limit is doing, and with the rules and theorems that we discussed in this section, should be able to calculate some of these limits. For instance, the limit as x goes to infinity of 2 minus 5 e to the negative x. Of course, we can use property of limits to evaluate each term. Limit of a constant is just a constant. And I can pull out the multiple outside the limit. And we know from before that the limit of e to the x, or e to the negative x, in this case, as x goes to infinity, is just 0. Right? So that makes that whole term 0. So 5 times 0 is 0. Given as the limit equal to 2. So then this is where those properties from above come in handy, right? We've seen how to use number 1 on the previous 3 examples on rational functions. Now we're using here the limit of e to the x or e to the negative x. Okay, so make sure you know those and you're ready to apply them when needed. But we'll also have things that include trigonometric functions or inverse trigonometric functions. And in that case, some of those functions will have asymptotes, if you recall from your trigonometry class. So for instance here, the limit of 8 times x to the negative 1 as x goes to infinity is just the same thing as the limit of 8 over x, and thus just 0 from the theorem above, right? As x gets larger and larger, since you have a constant on top, this whole expression 8 over x just goes to 0. And the limit of our tangent of x as x goes to infinity is pi halves. So this whole limit is negative pi halves. So that's something you might want to just remember, recall from your trigonometry class. You have horizontal asymptotes of negative pi halves and pi halves for our tangent of x. So remembering those graphs come in handy when evaluating these types of limits.